welcome to RLC circuits in free oscillation. So recall the charge held by the capacitor in an RLC circuit. Can be modeled by the equation L Q double prime plus RQ prime plus 1 over C times Q equals E of T, where L is the inductance, R is resistance, C is capacitance, and E of T is the impressed voltage. A circuit is said to be in free oscillation. So an RLC circuit is said to be in free oscillation if there is no impressed voltage. So in this case, then the equation winds up being homogeneous, and the equation becomes L Q double prime plus RQ prime plus 1 over C Q is equal to 0. So solving for the general solution, we have characteristic equation L R squared plus capital R times lowercase r plus 1 over C is equal to 0. And so using the quadratic formula, we get that lowercase r is equal to negative capital R plus or minus the square root of r squared minus 4 times L divided by C all over 2L. Note here that that numerator is always going to be negative or have negative real component. So just a note, since R, L, and C are all positive constants, the real component will always be negative. And we have 3 cases that we can run into. So we get 3 cases, or 3 possible types of solutions. Just like we had with the free damped spring mass systems. So our first possible type of solution is again called underdamped. And for an underdamped system, this is where R is complex conjugates. So this is where R squared minus 4L over C is negative. So the roots are complex conjugates. And we have R is equal to negative R over 2L plus or minus I times the square root of 4L over C minus R squared all over 2L. So our solutions take the form y is equal to C1 e to the negative R over 2L times t times cosine of omega t plus C2 e to the negative R over 2L times t times sine of omega t. And here omega is that square root of 4L divided by C minus R squared all over 2L. Our second case is called overdamped, just like in the spring mass system. The overdamped case comes when we have distinct real roots. So in this case, R squared minus 4L over C is greater than 0. So we have distinct real roots. We'll call them R1 and R2. And again, note both are negative. And we get our solution takes the form y is equal to C1 e to the R1t. Actually, I'm going to write this as R1 is negative alpha and R2 is negative beta. So we have C1 as e to the negative alpha t plus C2 e to the negative beta t for our solution. Our third case is critically damped. Just like with our spring mass system, our free spring mass system, this occurs when R squared minus 4L over C equals 0. And so we have repeated real root. R equals negative alpha. And our solution is y is equal to C1 e to the negative alpha t plus C2 t e to the negative alpha t. So just like with our spring mass systems, note in each of these three cases, the limit as t goes to infinity of y is 0. So note in each of these cases, the limit as t goes to infinity of y of t is just 0. So this all of the homogeneous solutions essentially disappear as time passes. So now let's go ahead and consider an RLC circuit with resistance 20 ohms, inductance 0.1 henries, and capacitance 10 to the negative 3 farads, which has an initial current of 4 amperes and the capacitor has an initial charge of 2 coulombs. Our job is to find the current at time t if the impressed voltage is identically 0. So going through, we have resistance 20 ohms. So our R is 20. We have an inductance of 0.1 henries. So our L is 0.1. We have a capacitance of 10 to the negative 3 farads. So our C is 10 to the negative 3. We have impressed voltage is identically 0. So E of t is always 0. Then we have initial condition. We have an initial current of 4 amperes. So we have I of 0 is 4. And then we have an initial charge of 2 coulombs. So Q of 0 is 2. So we can go ahead and set up our IVP. So setting up the IVP. We have 0.1 times Q double prime plus 20 times Q plus 1 over 10 to the negative 3rd times, 20 times Q prime plus 1 over 10 to the negative 3rd times Q is equal to 0. Then we have I of 0 is 4. We actually don't want Q's, so we have Q of 0 is 2. And Q prime of 0 is our initial current, which is 4. So we have our IVP. We can rearrange this. So this becomes 0.1 times Q double prime plus 20 times Q prime plus 1 over 10 to the negative 3rd is just 10 cubed, or 1000, times Q is equal to 0. And then this is equivalent to Q double prime plus 200 times Q prime plus 10,000 times Q is equal to 0. With initial conditions, Q of 0 is 2 and Q prime of 0 is equal to 4. Now solving the IVP, we have characteristic equation. R squared plus 200R plus 10,000 is equal to 0. This is just R plus 100 squared equals 0. So we get that R has a repeated root. R is equal to negative 100. So we wind up with our solution, our general solution. Is y is equal to C1 e to the negative 100t plus C2 times t e to the negative 100t. And plugging in our initial conditions. Sorry, that's not y. These should be q's. I apologize. Earlier in my video as well, we're not dealing with y's, we're technically talking about q's. So all of my solutions should have been with q's. So we had q is equal to solution q is equal to solution q is equal to. And then in each of these cases, the limit as time passes of q of t as t goes to infinity is equal to 0. All right, I apologize about that. Anywhere I wrote a Y, I should have been writing Q. I'm so used to solving equations in Y, it's automatic. All right, so plugging in our initial conditions. We had Q of 0 was 2, and Q prime of 0 was 4. So Q of 0 equaling 2 tells us that C1 plus C2 times 0 is 2. And we get that C1 is equal to 2. So we have Q is 2e to the negative 100t plus C2 te to the negative 100t. We know that Q prime is, that would be negative 200 e to the negative 100t. Then we would have plus C2 e to the negative 100t. And then we would have minus 100 times C2 times t e to the negative 100t. If Q prime of 0 is 4, this should be equal to negative 200 plus C2, and then that negative 100 C2 times 0 is just plus 0. So we get that C2 is 204. So our solution of the IVP is Q of t is equal to 2e to the negative 100t plus 204 t e to the negative 100t. Now, our actual problem, the initial problem, I apologize for the scrolling. The initial problem asked us to find the current. So we are now going to use the fact that the current is just the derivative of the charge. So now we will go ahead and find the current. And so we know that the current I of t is just Q prime of t. So we have I of t is just the derivative of 2e to the negative 100t plus 204t e to the negative 100t. We certainly could also just plug in our Q prime equation we already had, plugging in the numbers. But we have negative 200 e to the negative 100t plus 204 e to the negative 100t minus 20,400 t e to the negative 100t. And this becomes the current I of t is 4 e to the negative 100t minus 20,400 t e to the negative 100t. So this is our current based off of the initial conditions we were given and the resistance, inductance, and capacitance we were given in this free oscillation problem.